Hello, everybody. Mr. Hinnon here for some Henstitute notes. This one is on the electric force and Coulomb's law. So, with this, one of the things I started out with is I just wanted to do a whole bunch of just kind of a review of the stuff from the electric vocabulary. We know that our electricity started off with Thales of Miletus. He's the first one that recognizes that amber could actually attract different little pieces of straw and fur when it was rubbed against animal fur. And he's also, we didn't even talk about this, but he's the one that kind of looked at the fact that iron is affected by lodestones. Lodestones are basically the early magnetism. So he's kind of the first one that observed static electricity and magnetism. Then we have like from the 500 to 600 BC to the 1600s. So we have quite a bit of a change in time here. We have 2200 years. And then we get William Gilbert, and he's the first one that actually kind of started to coin different terms. So he used the word electricity based off of the electron, which is the Greek word for amber. He wrote it down in his book, started to conduct different experiments and that type of stuff. So that's where we started off at. Then we jump into Charles Dufay. He's the first one that probably did kind of our investigations. And one of the things I love about this, let's see if I can move this out of the way for a second, is he did a variety of different experiments and that type of stuff. I love this experiment over here. It talks about how they would take like a small boy and actually hook him up with threads down here, and that would keep him off of the ground. And then this is actually a glass rod that they've rubbed against some kind of cloth to charge it up. And then they would touch the kid, and then he would be electrified. He would be charged up, kind of like yesterday. Previously, when I did this with the Van de Graaff and I touched it, if you actually touched me when my hair was standing up, you would have gotten shocked because I had built up a static electric charge. So that's kind of what they did. I think that's kind of funny, probably giving money to those kids so they could do it, but just kind of a funny little illustration. Then we get good old Ben Franklin, pretty much at the same time as Dufay. He's just a better at writing everything down. So he and one of the people he worked with, Collinson, actually wrote down his experiments and observations on electricity. With this, he started to try to look at, okay, what about lightning? What is lightning? Is it the same thing as this electric phenomenon that we get around here where you rub materials together? And he actually, that famous experiment of flying a kite, his idea was he was going to put the kite up there so that it would actually be in the storm. So that's what this picture is kind of showing. This is the kite. The idea is we wanted to put it into a thunderstorm, and so it would build up a static electric charge. And then he had this cord running down to a key. And so if you're noticing here, we have little sparks of electricity off of the key. So that was kind of the idea of the experiment. Not a very safe one, a very dangerous one. Some of the data that I've read, some of the information I've read during that time is it was kind of hit or miss. Sometimes people got it to work, some people didn't, and they didn't actually usually touch it to themselves. They would actually do more of a, I don't know the best way to put it. They would store it. We're going to talk about capacitors and Leyden jars later, and they would store it in that Leyden jar. But he's the one that termed things like charging because of discharging a gun, batteries, electrify, conductors, all that stuff. And he thought of it as a single fluid that you would basically add the fluid or remove the fluid, and that's what made you positive or negatively charged. Interestingly enough, we're going to find out that he wasn't quite right, but it's at least a good start. And then we also have the law of conservation of charge. So a lot of things contributed to Ben Franklin. That's why we kind of consider him the founder or kind of the father of electrostatics. And then I threw in J.J. Thomson because I think it's very important. The fact that he used cathode rays and he noticed that they were actually made up of small little particles. And these particles were coming from the atom itself. Since you basically had a tube that had almost no air in it whatsoever, the only way this could possibly have worked is if you were talking about those charges or that light actually coming from the individual atoms. And these atoms, these cathode rays, were actually electrons. They were negatively charged particles inside of it. We'll do a demonstration in class, or I'll put an extra little video demonstration to kind of talk about cathode ray tubes and that type of stuff. So we should be able to kind of see that. And I just threw in some extra information about how other scientists kind of argue with him on what it actually was. And it seemed to work regardless of what the gas was. And the idea is you actually wanted very little gas in there so that it pretty much was just the beam of light. Then we get to the atom. So let's go into Bohr's model of the atom, which is the idea that we have these different particles that are in some kind of nucleus down here. So this is our nucleus. Whoops, I jumped back the page. So this is our nucleus here. And we now know that it has protons and neutrons. Pretty much all they would have known is that it was positively charged. And eventually we get these little electrons on the outside that are kind of orbiting. So couple of things that we have on here is we have the mass of the proton, we have the mass of the neutron, the fact that they're the major thing that cause mass. That electron here is so much smaller than these that we just kind of ignore it in terms of mass. It's about 1,000, 2,000 times less massive. But the thing that's very important that we eventually are going to get to is the charge on an electron. So this is the quantity of charge on an electron or a proton. Actually, we find out that they both have the same quantity of charge, and this value of 1.6 times 10 to the negative 19 coulombs. We'll talk later when we get into electric circuits why it's such a small number, why it doesn't have a value of 1. Also, a little bit later today, we're going to talk about where the Coulomb comes from. Why is that a particular unit? But that's a very important one. So pretty much our protons here are positively charged, but they have this value, and the electrons are negatively charged and they have this value. That's why in chemistry, we talk about just positives and negatives. So if you have equal numbers of them, then it is neutral. However, you can get different ions that normally we have equal numbers of electrons and protons, so they're electrically neutral, but you can add or remove electrons. This is the key thing. You're only adding or removing electrons. We're only moving electrons, and that's what gives it its net electric charge. And it's just going to be equal to the number of electrons you're adding or removing. So in this particular case, I've got 4 protons and 4 electrons. If I suddenly remove 2 electrons, we would say this has a positive 2 charge, or it would be positive 2 times that 1.6 times 10 to the negative 19 coulombs, and that would give us a 3.2 times the negative 19 coulombs, and that would be the quantity of charge on that atom. So we could actually figure that out. So it's a key idea that we're only moving electrons. This is one of the things that Franklin got wrong when J.J. Thomson discovered the electron and determined that it had a negatively charged. And it was negatively charged based off of what Franklin said. It made us understand that it's actually electrons or negative charges moving and not positive fluid. So that was one of the things that unfortunately Franklin didn't quite get right, but he at least started us on that idea. Then we get into this idea of how do I charge things up? What am I actually doing? And typically what we find is with Charles Dufay and William Gilbert, that all you have to do is do it through friction. If I just rub some materials together, I'm going to charge things up. And so it's possible to transfer charge by just rubbing materials together. And this is known as triboelectricity. Tribo means friction, and electricity is the fact that you're dealing with charges. And what we have is we have things like a triboelectric series here. And what they show you is that certain materials have more of an attraction for electrons or negative charge, and some have less attraction. So for example, our PVC up here is highest on the list. So it would be the most negative. It would be the one that would actually have a negative charge, whereas glass down here is a positive charge. So if you were to take glass and rub it against fur, so if I took glass and rubbed it against fur, for example, the fur would be negatively charged and the glass would be positively charged. Ebonite up here that they're talking about is actually close to this rubber material, and they're rubbing it against fur. So you'll notice that the ebonite since it's higher up on the list, is actually gaining a negative charge, and the fur is gaining a positive charge. So it depends on where you fall on this triboelectric series that allows you to talk about whether you become a net positive charge or a net negative charge. And so that's what we deal with when we're talking about, is something charged up. And then we talked earlier about the law of conservation of electric charge. Whatever electrons are leaving one material, so basically you have little electrons that are leaving this fur and they're jumping onto the ebonite. If I have one electron, then I have that 1.6 times 10 negative 19 coulombs moving. And so I don't create or destroy any charge. I'm only moving it from one place to the other. So overall, if these started out as neutral, overall they're still neutral. All I've done is I've kind of separated the charges. So this is kind of a separation of charge, but the net charge is still going to remain constant. That's very important as we do this. We've talked about this before. Like charges tend to repel, and unlike charges tend to attract. So if I have a positive and negative, they're going to attract each other, but two negatives or two positives are going to repel each other. So that's kind of probably the first idea that most people know. Later on, we're going to talk about electric flow and the movement of charges. Right now, we're talking about electrostatics, so we're not really talking about it as much, but they follow the same kind of idea. Like heat goes from hot to cold. So this is high temperature to low temperature. In our case, we're going to actually have electricity flow from negative charge towards positive charge. And eventually what we'll talk about is not temperature, we'll be talking about voltage. So we'll talk about high voltage and low voltage. So, but we'll talk about that later. And you can talk about what materials allow it to happen easily and difficult. The neat thing is your thermal conductors tend to be very good electrical conductors, and your thermal insulators also tend to be very good thermal insulators or electrical insulators. So they're kind of matched up. It's very interesting that they follow that. Then I have some things about charging by contact and by induction. And here's what I mean by that. So if I have something that's charged and I bring it near something else, I actually will induce a temporary charge in this. So this piece of plastic might have actually just been neutral and not have any charge. But by bringing something that's negatively charged, what it'll do is it'll actually cause the surface to become positively charged, and therefore it has temporarily induced an induction of charge. So we talk about this inducing a charge. A good example of this, if you've ever taken a balloon and rubbed it on your hair, sometimes you can stick it against the wall. And if you rub it against your hair and you stick it against the wall, that'll allow you to actually induce a charge in the wall, and then those opposite charges will actually attract each other. The latex or the rubber of the balloon, rub it against your hair, the balloon would become negatively charged, kind of like this ebonite rod. The wall will be inducing a temporary positive charge, and you can actually get them to stick together. So it's kind of neat if you've never done it before. This is just another example that if you actually take something that's charged, so if this was charged, for example, and I touch it against myself, I would actually give it the same charge. So this is just charging by contact, where they gain the same charge. And then you can also charge by induction. So if I bring it nearby, so let's say I brought this next to my can, and then I come along and I touch this to the ground. So I actually touch this while this charged object is nearby, and then I kind of remove everything. I would actually make this be the opposite charge. So I can actually make this be positively charged. And that's permanent induction. And the basic idea is induction deals with this idea that you're going to give it the opposite charge. Then we get into Charles Coulomb, Charles Augustin de Coulomb. He's the one that actually started investigating pretty much about a contemporary of Franklin, but he started investigating the actual calculations. How do I actually find it? And so using some of Joseph Priestley's ideas of electrical repulsion, he wanted to come up with measurements, ways to actually measure this electrical force. And he actually was able to do it. And the key things that he established, which are kind of neat, is that it was an inverse square law with distance. That very similar to Magnets actually follow this as well. And so both of these kind of fall into the same category. Poisson actually did some with magnetic forces, and how that kind of fit in there. And then because of this, we give the unit of electric charge the Coulomb, named after good old Charles. And the equation he came up with actually kind of borrowed a little bit of Newton's law of gravity, because if you remember, the force of gravity equation for Newton was that the force of gravity was big G times mass 1 times mass 2 over the distance between them squared. So this is universal gravitation law that we learned back in chapter 5. Guess what? Coulomb's law looks almost the same, except this is now some kind of electrostatic force. It has a different constant. So this K, the electrostatic constant, actually has a value of 8.99 times 10 to the ninth. This big G up here was a totally different number. It was 6.67 times 10 to the negative 11. And it was Newton's meters squared per kilogram squared. But this is 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. Now, I left this on here because we're going to talk about this later, that we also talk about this thing called the permittivity of free space. It's a constant. It's a natural constant of the universe that we'll actually use to kind of go over some of our ideas a little bit later. But it's related to K with this 1 over 4 pi, but don't worry about epsilon 0 right now. It's just you concentrate on K. K is 8.99 times 10 to the ninth. And then Q1 and Q2. So they use Q to represent the quantity of charge. So this would be the quantity of charge on object 1, and this is the quantity of charge on object 2. So we're not worried about whether they're positive or negative. We're just worried about the quantity of charge. In other words, how many coulombs they have. That's why the absolute value is on there, that we kind of drop the sign. And then R is actually the distance between them. So if I measure from one over to the other, that's my distance. So it's an inverse squared law. So this is actually our main equation that we'll be kind of playing around with here. So to finish things out, what I wanted to do is just do a couple little example problems. See if we can actually kind of knock these out. So if I start out, I have the model of the hydrogen atom. It basically has a proton in the center, and it has an electron on the outside. And we imagine that it's kind of orbiting kind of like a planet. So let's assume we know that the average radius of our electron here is this 5.929 times 10 to the negative 11 meters, and then we're going to ask some questions on it. So let's assume one extra little thing, that we want to figure out the force. Is it an attractive or repulsive force? Well, the only way to figure out whether it's attractive or repulsive is to look at the signs. So that's why we use the signs on there. So since the proton is positive and the electron is negative, that means it's an attractive force. So nothing fancy there. The magnitude of the electrostatic force, this is part B. Now we're going to use the equation up here. So when we do part B, we're going to actually plug it into the equation. So we'll plug in K, 8.99 times 10 to the 9. Then I have the quantity of charge on the electron and the quantity of charge on the proton. They both actually have the same quantity of charge. That's that 1.6 times 10 to the negative 19 that you saw earlier. That's how many coulombs you have. 0.6 times 10 to the negative 19 coulombs. We'll talk later when we deal with electric potential where that number comes from. Another scientist, actually an American scientist, not Ben Franklin, actually determined that number. And then on the bottom, we're actually going to divide by the distance between them squared. That's this average radius that we have, this 5.29 times 10 to the negative 11. Just don't forget that that is actually squared. Chunk that out. That'll tell us how much force of attraction there is between them. Now, I threw in C, just kind of an extra little thing, because I was talking about this in my Physics 1 class. We're talking about circular motion. So I thought, hey, why not do circular motion here? So it says, what is the speed of the electron, assuming that it's a circular orbit? So you could actually find this C, this speed, but what you would do is you would say, hey, this force is actually a centripetal force. This attraction between these things, this electrostatic, is actually also your centripetal force. And centripetal force is mass times speed squared over your radius. So I could rearrange this and find how fast the electron is going by actually taking the force we just calculated, the electrostatic force, multiplying by the radius, and then dividing by the mass of an electron. So make sure we're doing the electron down here. So it'd be whatever force we just calculated up here, the radius of 5.29 times 10 to the negative 11. And then on the bottom, we'd have 9.11 times 10 to the negative 31st, because that's actually the mass of an electron. So we can calculate how fast it should be going. Now that was v squared. So realize that when I get done, I'm going to actually have to square root this to figure out v, but just kind of an extra little tidbit that I thought was kind of neat. So a couple of things that we kind of get into as we are looking at that. I wouldn't ask you something like C normally. I just want to know A and B. But that's kind of the beginning. That's Coulomb's law. That's kind of the beginning of it. I have one other little sample problem I want to kind of look at and talk about how I would set this one up. So it says I have three charges on a line. It says determine the magnitude and direction of the net force on Q1. So Q1 is the one in the middle. The first thing I would kind of look at is what is going to happen in terms of direction of these forces. So since it's a positive charge and these other ones are negative charges, what this tells me is that it would feel a force in this direction between these two because it's attracted to Q2. And then they would also, let's do a different color here. It would also feel a force over here. If these two forces were the same, then the net force would be 0. But I don't know if the forces are the same. To figure out this force, this is the force to the right, I would have to take K, the 8.99, times 10 to the 9th. I'd have to multiply it by the mass of this, or not the mass, but the charge. Now notice it's got this funny looking mu on there. That actually means we're going to use our prefix of 10 to the minus 6. So this is 3 times 10 to the minus 6. And then I would actually have this one, which is 7 times 10 to the minus 6. I don't actually put the negative sign on there and then divide by the distance between them. Don't forget that distance is squared. So that would be the force to the right. Over here, the force to the left would actually be, it's going to still be the 8.99 times 10 to the 9th, but it would still be this charge, 3 times 10 to the minus 6, and then it would be this charge, so it would be 4 times 10 to the minus 6, and then divided by how far apart they are, which is 0.2. Don't forget that that's squared. Now, if those two forces are equal to each other, then the net force would be 0. But to actually find the net force, I'd have to actually take the difference between those two. The reason why I would take the difference is because I'm talking about going, basically the net force would equal the force, let's say force to the right minus the force to the left. Technically, it's the sum of them, but I usually think of like something to the right as being positive, something to the left as negative. So it's kind of like adding a negative. I'm not going to finish out the numbers. You are free to calculate it and see what kind of numbers you get. I threw some things into our Google form to kind of answer. That's a little bit on our notes. Hope you enjoyed this edition of the Henstitute. Take care.